Well, I'm delighted to talk to you here today, especially because I'm going to introduce you to acoustics and the effects of meteorology on acoustics. And yeah, obviously I'm the only speaker here on acoustics. Well, as Beth already said, I work here on at Eindhoven University of Technology at the Department of the Built Environment. I'm in the Building Acoustics group. And we focus on several areas in acoustics, as room acoustics, building acoustics and vibration, but also on urban acoustics. And that's, of course, where this work is related to. Urban acoustics is my main field. Well, we share our laboratory with a spin-off company at the university, Level Acoustics, and it creates an interesting interaction between, at one hand, fundamental research, and at the other hand, application and real-life projects. Well, our own chair of building acoustics is rapidly growing. Currently we have 7 PhD students. Bert Blokken is our ad interim professor, and I'm an assistant professor in this group. Well, today I will talk about the importance of urban acoustics. Well, urban acoustics has positive effects. Think about parks in urban areas where you can recreate. But a lot about urban acoustics is also the down effects, the effects of noise, and that's what I will talk about today. And what we do as acousticians to this is to study the physical effects in the propagation between noise sources, mainly they are the road traffic, and the citizens. And I will shortly address how what research we are carrying out at Eindhoven University on this area. And then the main topic here in the presentation, meteorological effects, air absorption, mean wind and temperature effects, and also atmospheric turbulence. How do they affect sound propagation? I will conclude with challenges rather than with conclusions. So, health effects due to environmental noise. The World Health Organization pays quite much attention to this, to health effects, and in 2011 they published this report, Burden of Disease from Environmental Noise. And it quantifies the adverse health effects of environmental noise. And these health effects are related to that: cardiovascular diseases, annoyance, cognitive impairment in children, sleep disturbance, and tinnitus. And the WHO, they quantified it with the DALYs. It is daily disability-adjusted life years. So it says how many healthy life years are lost per year in Europe. And it's due to premature death and also due to the states of poor health of disability. Well, if you sum up all these healthy life years lost, then in total we come up to like 1.6 million years lost. So it's a big problem, urban noise. And also traffic, road traffic, rail traffic, air traffic, it's not expected to decrease in the near future. So what is Europe doing with this? We have the European, the Environmental Noise Directive, END. It started in 2002, and with this directive, in Europe we try to avoid, prevent and reduce negative effects caused by environmental noise. We do this by mapping, so every city in Europe produces noise maps, yearly average levels. All cities in Europe need to have action plans how to deal with the noise in the city, and needs to communicate this with the public. And also we're trying to develop a long-term strategy in Europe. Well, one of the problems is that the software that's used to produce these noise maps is quite approximate, and it's not giving the correct picture. So there's already an opening for more research at universities. So, as already said, we as acousticians, we work with the propagation effect. So from the sources to our citizens. Important is the ground effect, so absorption by the ground surface, shielding, think on noise barriers, for example, effects of urban topology, and an important thing, meteorological effects. So here at TUE Eindhoven, we work both with computational methods. It's a big part. We try to develop our own methods that predict sound propagation, and also we develop experimental methods. And thereby we work with oralization. Oralization is similar to visualization. So with oralization you can make audible an environment which you're designing. And we work with vegetation. So for example, green roofs, green building facades, to reduce noise. We study meteorological effects, urban topology, and a topic that I won't talk about today, human echolocation in blind people. So currently there are 3 PhD students and 3 additional researchers, apart from me, that work with this in this field in our group. Well, meteorological effects. What do we have? How does meteorology affect sound propagation? Well, we have air absorption. Due to viscous friction and thermal heat conductivity, energy from the acoustic wave is consumed. And this consumption increases with acoustic frequencies. So for higher frequencies, there's more absorption. So for sources at long distances, airplanes, you mostly hear the low frequencies, mostly because of this relation between absorption and frequency. There's another part that makes it more complex, and that's the relaxation and compression effects. And this is nothing else than that when energy, when new acoustic energy arrives at molecules, then this energy has to be redistributed. It's different for different molecules, so it's different relaxation times. This is non-linearly proportional to the frequency. So if we look to the absorption as a function of frequency, we see that for different relative humidity, so for different compositions of the molecules in air, we have different absorption, which makes it important to know these ambient conditions in order to predict the effect of absorption. Well, the other effect is what we call refraction, so how sound waves are bent due to mean wind speed profiles and mean temperature profiles. Well, these profiles are much more familiar to you than to me, but what for us as acousticians is important is to know how the profiles are in the atmosphere. So what happens with the acoustic wave? Think about the sound speed. The sound speed is dependent on the temperature. So for higher temperature, sound speed is larger. For lower temperature, sound speed is lower. So if you look in the upper picture here, then here we have a higher sound speed, here we have a lower sound speed. And this vertical line here is the phase of the sound velocity, and the sound travels perpendicular to the wavefront. And as it travels perpendicular, we get a curved sound ray. And the sound ray is bent towards the area with the lower sound speed. So this is happening in the atmosphere. So depending on the sound speed profile, and the sound speed profile is affected by the wind and the temperature, sound propagates downward or upward. And of course this also depends on frequency, this depends on the strength of wind and so on. As an example, here's a calculation for a sound source over a hard ground surface, and for one frequency, so a single tone. On the left picture, what you here see is an interference pattern. So here you see high levels, you see low levels, that just because of the interference between the direct sound and the reflection of the ground. Here we see at this 300-meter position from the source, as a function of the height, we see the levels. You see the low levels here due to interference, and higher levels near the ground. Now, if we have what we call upwind, so wind from the receiver to the source, sound waves are bent upwards. So here we have very low levels in this blue area. If we have highway and we have wind from us to the highway, then we hardly hear the highway. The other direction, levels close to the ground are much higher. Well, in Eindhoven we work with models that we developed to predict these effects. A special case is nocturnal boundary layer. In summertime, in the mornings, then all sound waves are bent downwards in all directions, because we have this temperature profile close to the ground. Well, what is the consequence of this? Well, if we have noise barriers, then sound waves can propagate over noise barriers. So in the Netherlands, with west wind dominating wind direction, if a noise barrier is designed in an unlucky way, we could have a low performance of noise barriers. So we work with this and quantify the effect, and the effect can be really large. So that's refraction. Well, the other aspect I would like to talk about is turbulence. So atmospheric turbulence actually has the same effect as mean wind profiles, but then on a very small scale. And due to the randomness, the effect on acoustics is that we have a phase change of the sound wave, and we have amplitude changes. So if we go back to these figures again that I showed for refraction, if we now have turbulence, one effect is that for the case without wind, so it's only turbulence and no strong profile, we see that this interference effect is not present any longer, or much less present, so it's decorrelated, the sound waves. But also an important effect of turbulence is that if we have upwind, so wind from source to receiver, so very low sound levels close to the ground, if we have turbulence, then sound is scattered into this shadow zone. So the levels are not as low as we would predict with a mean wind effect only, but atmospheric turbulence causes that we have sound is smeared out over our shadow zones. An effect of this is an experiment from my colleagues in Sweden, where they have measured sound propagation over a tall barrier, and this upper line here is what they found, and they could only reproduce these levels by including atmospheric turbulence. So without the turbulence effects, levels were much lower, and they need to include turbulence to predict the effect. What are the challenges in this area? Well, currently we had a master student visiting the EMPA laboratory to quantify the effect of sound propagation over more complicated urban forms. So previously we only studied like simple noise barriers, but we're interested if sound propagates over a building block with a gabled roof, how it interacts with wind and sound. Colleagues in Japan have studied in this line. They have done a 3D simulation of an urban topology, and especially in the right picture you see that we have wind from this direction, and you see that the color is the effect of wind, and you see here that there is much higher levels than on the left side. Another challenge is to include the correct CFD approach. Well, acousticians that work in this field, they tend to use simplified CFD approaches because they can handle it. But for complicated situations, it might not be appropriate. So here we studied sound propagation in over urban street canyons, including the wind effect on it, to study if, for example, RANS was sufficient in this case. Finally, we work with efficient modeling approach. Calculating sound propagation is very time-consuming, and we have an open source project running for many years, where we work with development and the open source program to present an efficient method for sound propagation. That concludes my talk. Thank you very much.